Hello and welcome back to the Science of Concrete Materials class. This is lecture number 10 of the class. We will continue our discussion on the cement module of the class and the hydration subject. This lecture's topic is the hydration products and their properties. Last lecture we discussed the Portland cement hydration and mention the hydration products. Today we will discuss their properties in detail. The various hydration products that are formed in hydrated cement paste, have quite diverse properties, and the behavior of each compound will contribute to the overall behavior of the cement paste. In this part, we will briefly review the properties of the individual hydration products, a review of their physical interrelationship will be discussed, after we study the microstructure development in coming up lectures. Again, this is a summary of the hydration products shown here. This slide I have shown before, but I'm showing it here again as a refresher. In this lecture, we will mostly focus on the solid products right here, and the voids and the water will be discussed in details in the development of the microstructure lectures. Okay, so the first and most important hydration product is the calcium silicate hydrate. The calcium silicate hydrate phase, we abbreviate it as C-S-H. It makes up 50 to 60% of the volume of the solids in a completely hydrated Portland cement paste. And so it is the most important phase determining the properties of the paste. The fact that the term CSH is hyphened signifies that the calcium silicate hydrate is not a well-defined compound. For example, the calcium to the C to S, which is calcium oxide to silicon dioxide ratio, varies between 1.5 to 2, and the structural water content varies even more than that. The morphology of the calcium silicate hydrate also varies, from poorly crystalline fibers to a reticular network. So due to their colloidal dimensions and a tendency to cluster, the calcium silicate hydrate crystals could only be resolved with the advent of the electron microscopy. In older literature, the material is often referred to as calcium silicate hydrate gel, and I have used this term often, if you noticed. The internal structure of the calcium silicate hydrate, also still remains unresolved. Previously it was assumed to resemble the natural mineral called tobermorite, and that is why the calcium silicate hydrate, and you might see it in some references, called the tobermorite gel. Okay, again, although the exact structure of the calcium silicate hydrate is not known, several models have been proposed to explain the properties of this material. The suggestion is that the model ranges from colloidal to layered structure. According to Power's model, the material has a layer structure with a very high surface area. Depending on the measurement technique, surface areas on the order of 100 to 700 square meter, meter square per gram was reported. it also, the strength of the material is attributed mainly to the van der Waals forces. And I have mentioned that before. Also, the size of the gel pores, or the solid to solid distance, is reported to be about 18 angstrom. There is a model by the Feldman-Sereda model, visualizes the calcium silicate hydrate structure as being composed of an irregular, kinky array of layers, which are randomly arranged to create interlayer spaces of different shapes and sizes, between 5 to 25 angstroms. Here on this slide here, I summarized, the properties of the calcium silicate hydrate product. As you can see here, what I just mentioned, just summarized here, where the strength comes from, from covalent and ionic bonding, and also van der Waals bonding. This is, the primary strength given phase in Portland cement concrete. So that's why we care about this product so much, because it's what contributes to the strength of the concrete. Here is a photo taken under a scanning electron microscope, and you could see the colloidal random nature of this product. And on this slide, as I mentioned about the layered structure, this is just a schematic to show or to present what has been proposed about its structure, which is a distorted layered structure. As you can see, actually, it has been proposed similar to a clay mineral, but it's not crystalline. So look at this first part of the schematic here, which is well crystallized clay mineral, as you can see here, and here a poorly crystallized calcium silicate hydrate gel. I will keep referring to it as that. So here it shows, these are the layers, for example, containing the silicon dioxide, the calcium oxide, and the hydroxyl ion. The P refers to the capillary pores, the M, the micropores, and the interlayer pore. We will talk about that more later. Here's another schematic showing, it's a model showing what is believed this structure to be composed of. As you can see here, for example, it shows the type of bonding and the porosity within this structure. For example, these lines represent the calcium silicate layer. Let me go back, as mentioned here. These here, for example, shows right here the adjacent layers, the covalent bonds. Here, for example, shows where van der Waals forces, bonded by van der Waals forces, according, something like this. For example, here where these X's are adjacent layers bound by oriented water molecules, between the layers, some of these. Here, adjacent layers held together by a restricted water film, in this case, here, these bubbles. And here it shows, the porosity. We have, the bulk water in the capillary pores. Here, water molecules in micropores or physically absorbed on the external surfaces, under surface forces, but these are mobile, these water molecules. I keep going. The X's, this represents water in very small micropores between the calcium oxide, the silicon dioxide layers, or interlayer water molecules. These located at special sites on the internal surfaces between the layers, not very mobile. Don't worry, we will talk about this in the microstructure lectures. There are more details coming up. I'm just mentioning them here so that you get introduced to the terminology. Okay, the second product of interest is the calcium hydroxide. Calcium hydroxide crystals, also referred to or called portlandite. That's the mineral name. It constitutes 20 to 25% of the volume of solids in the hydrated paste. Now, in contrast to the calcium silicate hydrate, the calcium hydroxide is a compound with definite stoichiometry, which is, as you can see here, the calcium hydroxide, which is the calcium with the hydroxide ion. So it has a definite stoichiometry. The calcium hydroxide, tends to form large crystals with a distinctive hexagonal prism morphology, as you can see here. The morphology usually varies from nondescript to stacks of large plates, and its presence, affected by the available space for it to form, the temperature of hydration, and also the impurities present in the system. As compared with the calcium silicate hydrate, the strength contributing potential of calcium hydroxide is limited as a result, of the considerably lower surface area, because it's well crystalline, the surface area is much lower. Okay, so again, just to summarize, it has much lower surface area, does not contribute much to strength. It has an advantage. It keeps the pore solution alkaline, and high alkalinity is good when we talk about corrosion. Also, it has another advantage. It blocks the capillary pores, which means it lowers the permeability. We will see that later. Also, it has some drawbacks. The presence of the calcium hydroxide is prone to leaching in water, which will cause efflorescence. And also, its presence will make the concrete vulnerable to carbonation, as we will see later, and acid attack. As we will discuss those when we talk about the durability. Okay, the next products are the calcium sulfoaluminate hydrate phases, which you can see here. The AF sub T, AF sub, this one refers to ettringite, and this one to the monosulfate phase. The calcium sulfoaluminate hydrates, occupy about 10 to 15% of the solid volume in the hydrated paste. And because of that, they play only a minor role in the microstructure, but not necessarily in the properties. Okay, so they do not contribute much to strength. The formation of ettringite, in particular, does influence the setting time. And as we mentioned before, as a related topic, the high heat of hydration coming from the C3A can be favorable or unfavorable depending on the application. Remember when we talked about the heat of hydration curve, and we mentioned the high heat generated sometimes is useful in cold weather concreting. It has already been, stated, before that during the early stages of hydration, the sulfate to alumina ionic ratio of the solution phases generally favors the formation of the trisulfate hydrate, which is the ettringite, the C6AS bar 3 H32, as you can see here. This is also referred to as ettringite, as I mentioned, which forms needle-shaped prismatic structure, prismatic crystals, as can be seen here in this micrograph under the SEM microscope. In paste, of ordinary Portland cement, ettringite eventually transforms to the monosulfate hydrate phase I'm showing here, which is C4A S H12. These, form hexagonal plate crystals. The presence of the monosulfate hydrate in Portland cement concrete makes the concrete vulnerable to sulfate attack, as we have mentioned before. And again, it should be noted that both ettringite and the monosulfate contain small amounts of iron, which can substitute the aluminum ions in the crystal structure sometimes. Okay, so again, just to emphasize a couple of points, the ettringite, if it forms after the concrete or the paste has hardened, it could be harmful because it is expansive and could cause cracking and disruption. The presence of the monosulfate aluminate, which is actually how ettringite forms after the concrete has hardened, it's vulnerable to sulfate attack. If it's exposed to a sulfate source, it converts to ettringite and it causes a problem. Okay, this is here a photo of the monosulfate. It looks like these rosette clusters, as you can see. One more product we will talk. Actually, it's not really a product. It's a remnant, which is the unhydrated cement residue. Still, we will, even after long period of time, we will still have some unhydrated cement residue in the concrete or the paste, as we mentioned earlier in the previous lecture. The unhydrated residues of large cement grains may, as I said, may persist in well-hydrated pastes. The occlusion of the calcium hydroxide may preclude complete hydration, or there may be insufficient free space. If you remember, we talked about availability of a space for the cement to continue hydrating and forming hydration product. Nonetheless, it's there, and it has been shown by microscopy that it will remain for an extended period of time. Okay, this table here summarizes the hydration products and their properties, and as you can see, what I have talked about, but just this is a good table to summarize everything. We have the calcium silicate hydrate, the volume of fraction of the solid in the hydrated paste, about 65% of average. Its density, 2000 kilogram per cubic meter. The particle dimensions, we said, across it's less than 1 micrometer, and it's less than about 0.01 micrometer thick. The surface area, we said, between 100 and 700, on average about 400. Its morphology and crystallinity, it's a regular foil, amorphous, microporous. The calcium hydroxide, about 20% of the solid volume. Density 2250 kilogram per cubic meter. Its dimensions about 100 micrometer across and 10 micrometer thick. Surface area very low, as you can see. Its morphology, thick hexagonal plates that cleave easily and they are well crystalline. The monosulfate aluminate phase, about 10% of the solid volume. Density 1950 kilogram per cubic meter. Dimensions, roughly 2 micrometers across, 0.1 micrometer thick. Surface area very low as well. its morphology and crystallinity. Very thin, irregular plates clustered in rosettes, as I have shown in the previous slide. Fairly crystalline also. Unhydrated residues about 5%. Of course, this is the density of the cement. The particles roughly 1 micrometer. Surface area about 0.1 meter square per gram. And its morphology, of course, this is remnant of the original cement. So whatever the morphology of the cement, that's it. That is. This table here summarizes the influence of the paste components on the the influence of the paste components on the paste properties. As you can see, the component name right here, how it impacts the strength, deformations, and durability. Let's just go over these quickly. Calcium silicate hydrate, provides a major cohesive force, but it is intrinsically weak because of microporosity. But overall, it provides the strength. Dry concrete is stronger than wet concrete, because of stronger van der Waals bonds. Deformations, the water loss, as we will see later, from the micropores causes shrinkage on drying and creep on loading, at room temperature, that is. Durability, it's durable, very insoluble. The water in the micropores does not freeze and has low mobility, low permeability. Calcium hydroxide, how it contributes to strength, because increased porosity decreases strength, as we will see later. So it contributes to strength by reducing porosity. And the cleavage may limit strength of high strength paste. The presence, it might be harmful in this case. Deformation, it is dimensionally stable and will help restrain the calcium silicate hydrate deformation. For durability, okay, it blocks the capillary pores, and because of that, it lowers permeability, and that improves durability. But if slowly leached by water, will cause efflorescence, and this will increase permeability. Also, the carbonation and the attacks by acids rather, makes it also harmful in this case. The monosulfoaluminate phase, okay, this is in strength, it's not really very significant, but it reduces the total porosity overall, and that might help, but not much. And the deformation, not much of an effect. For durability, I mentioned this many times, it causes sulfate attack, by reforming ettringite and causing expansion. This is a big deal in sulfate attack. The unhydrated cement, for strength, it's only significant in low porosity pastes. It helps. For the deformation, the same thing here. It will restrain the calcium silicate hydrate deformation. Durability wise, if there is a renewed hydration later, it may cause autogenous healing of internal microcracks. I wouldn't count on this much anyway. The pores, I mentioned the pores as part of the products. I will mention what they contribute here. The capillary pores, as I said, the overall porosity helps, it impacts the strength. So the total porosity is the major factor in influencing strength. Less pores means higher strength. For deformation, the fine pores contribute to shrinkage and creep, as we will see. This is very important, and we will talk about it later. For durability, again, its influence comes from its influence on the permeability and diffusivity. So large pores increase water flow through concrete, and that is harmful. Okay, so anyway, just wanted to show this table because really it summarizes everything almost I talked about in the lecture. Okay, so this is really the end of lecture 10. Next time we will start on the development of the microstructure. Until then, thank you for listening, and I will see you next time. Thanks.